So we're on page 3, and we're starting to talk about mole ratio. The first thing, we just finished talking about the balanced chemical equation. And here's why it's important. The balanced chemical equation allows us to find the mole ratio. So the mole ratio is really a conversion factor, and it's derived from the coefficients of the balanced equation. This is where that balanced equation or that recipe becomes absolutely important. So this is the ratio between the numbers of moles of any two substances in the balanced chemical equation. If you look at the skeleton equation for the Haber process, it's not a sufficient recipe to produce any ammonia. There's just not enough hydrogen. We have enough nitrogen, the hydrogen's insufficient. We can't produce a single ammonia molecule. Once the equation is balanced, we can make some observations about quantities. So we have to have 3 hydrogen molecules for every 1 nitrogen molecule. If you look at the coefficients, 1 nitrogen molecule could produce 2 ammonia molecules. 3 hydrogen molecules are required to produce 2 ammonias. And so these are all based on the coefficients. So we're going to write some sample mole ratios. So here are some mole ratios between nitrogen and ammonia. So for every two moles of ammonia, we need 1 mole of N2 nitrogen. And you can look at it the other way. For every 1 mole of nitrogen, you need 2 moles of ammonia. I'm going to switch colors so we can see what's going on. The mole ratio is between hydrogen and ammonia. So look at the coefficients. For every 2 moles of ammonia produced, we need to have 3 moles of hydrogen. And the reverse of it, 3 moles of hydrogen are required to make 2 moles of ammonia. Then we have the mole ratios between nitrogen and hydrogen. So for every 1 mole of nitrogen, we need to also have 3 moles of hydrogen. And for every 3 moles of hydrogen, 1 mole of nitrogen. Take a look at these numbers again. Every single one of these numbers came from the balanced equation. Anytime you see ammonia, it has a 2, and that 2 comes from here. Anytime you see hydrogen, it has a 3. The 3 comes from the balanced equation. Anytime you see nitrogen, it's a 1. That 1 comes from the balanced equation. A mole ratio can be made between any two substances. Any two substances in a balanced chemical equation. The mole ratio is used as a conversion factor. The starting substance in the calculation will be on the bottom. The substance that will be in the answer will be on the top. And this is very important. Substances must be in units of moles to use the mole ratio. Must be in units of moles. So example 2, these come from the equations that we balanced on the previous page. Write the mole ratios from the balanced equation. So the first one, we had the decomposition of water. And you can look on the previous page, but it was 2 waters creating 2 hydrogen gas molecules and 1 oxygen gas molecule. So some mole ratios here. If we want to relate, let's say, water and hydrogen, they both have coefficients of 2. And you could also flip this one upside down if needed. 2 moles of hydrogen per 2 moles of water. You could compare water and oxygen. 2 moles of water for 1 mole of oxygen. Or you could flip it upside down, 1 mole of oxygen per 2 moles of water. And these both relate the reactant with one of the products. You can also relate 2 products to themselves. 2 moles of hydrogen for 1 mole of oxygen, and 1 mole of oxygen produced for every 1 mole of hydrogen produced. 2 moles of hydrogen produced. Then we have the formation of rust, or the synthesis of iron 3 oxide. Here's your balanced equation, and you can relate the amount of iron with the product. 4 moles of iron, with my 4, for every 2 moles of Fe2O3. And of course you could flip that upside down if necessary. You could relate the oxygen with the product. So 3 moles of O2 for every 2 moles of iron 3 oxide. And again, you can flip it upside down when necessary. Like we did above, you can also use this to compare the 2 reactants. If you have one, you need to know how much of the other. So for every 4 moles of iron, we need 3 moles of oxygen. And upside down, for every 3 moles of oxygen, we need 4 moles of iron. All of these numbers come from the balanced chemical equation. They're the coefficients. They have to come from the balanced equation. If your equation is balanced incorrectly, it will have serious effects for any stoichiometry calculations. You're going to have a lot of problems. Just like if you get the formula wrong, you get the molar mass wrong. If you get the balanced equation wrong, you'll get the stoichiometry wrong.